So what I did in the last class was talk about polar polytopes or dual polytopes, and basically what I want to do today, because I have the feeling that probably not everyone has seen that video yet, so I wanted to just say something that is related to that, and it's kind of self-contained, and then basically I want to take a little bit of a break and do something unrelated to the last 3 lectures to give you guys time to catch up over the weekend if you need to. Okay. So let's go back to the discussion between a polytope and its polar polytope or its dual polytope. Okay. So maybe I'll just write the definition that if we have a polytope P in Rd, then the polar, so this is a polytope, then the polar or the dual polytope is denoted like this. And it consists of the points such that, so let me just write it like this. So the vectors such that their dot product with any point in the polytope is less than or equal to 1. Okay? And there's an example that is familiar to you guys, which is the example that I drew over there of how the cube, this is supposed to be a cube, and this is supposed to be a regular octahedron. These are dual to each other. Okay, these are polar polytopes. And one thing that I explained last time is that actually these polytopes really live in dual spaces, which is this concept from linear algebra. You want to think that this is kind of your main vector space, and this is the dual vector space, which consists of the linear functions on this vector space. Okay? If you want to think about this in a very concrete way, I said that you want to think of the points in this space, the main space, so this is R3. Okay? We have always been thinking of the points in here as column vectors, and this lives in the dual space, and it's useful to think of these as row vectors. Okay? The reason being that when you do this C dot X, okay, then you can think that X is a column vector and C is a row vector, and then you can just multiply them, and the dot product is just the product of matrices. Okay? And what I proved last time is something that I already mentioned earlier, which is that if you have the vertices of your main polytope P, then you can get for free the inequality description of the polar polytope. It's exactly the same matrix. Okay, so this is the convex hull of these column vectors, and these are the inequalities defining the dual polytope. So for example, this says that y1 plus y2 plus y3 less than or equal to 1, etc. Okay, and vice versa. If you have the inequality description for this guy, ax less than or equal to b, then this matrix A, if you look at the rows of that matrix, those are going to be the vertices of the dual polytope. Okay? So vertices here become facets there, or inequalities there, and inequalities here become vertices there. Okay? And so what I wanted to do quickly is just explain a theorem, and it's actually a corollary of what I did last time. So if maybe you haven't seen the last video, then it's good if you look at the proof of last time, and then from that it follows easily what I'm going to say here. So let's say that my polytope is the convex hull of V, and it's given by the inequalities ax less than or equal to 1. Okay? And so then the dual polytope is given by the convex hull of the rows of A, and it's given by, let's say, P of V comma 1. Okay, so that's what I'm saying there. That the vertices of P become the inequalities of the dual, and the inequalities of the dual become the vertices of, sorry, the inequalities of P become the vertices of the dual. Okay? So that's and so now what I want to do is look at a face. So consider a face F, okay? And now how can you describe a face of a polytope? Well, you can describe it in two ways because it is a polytope. You can describe it as vertices or as inequalities, okay? So as vertices, let's say that my face is given by the convex hull of V prime, where V prime is just some subset of V. Okay? And how do I describe the inequalities of my face? Well, the inequalities of, maybe let's write, let me first write that this means x, these are the x's such that ax is less than or equal to 1, right? So far I'm describing my polytope P. Those are the inequalities of P. Okay. Now, if I want to describe a face, then what I can do is just say which are the inequalities that are actually equalities on that face. Okay. Maybe let's do this very concretely. So, for example, if let's say that I want to describe a face here, F. Okay. Then one way of describing it is as the convex hull of its vertices, right? And the vertices are 1. This point is 1, 1, minus 1. So it's this one. Okay? And this point is minus 1, 1, minus 1. So it's this one. Okay? So I'm saying that F is the convex hull of V prime. In other words, what I have here is V prime. These two guys. Okay? So that's the vertex description of F. But if I want the inequality description, then basically what I have to do is say, okay, well, these are the 6 inequalities of my cube, but on here, 2 of them are equalities because this face is on this face of the cube, which is where x2 is equal to 1, right? So this is an inequality that actually becomes an equality, right? x2 is equal to 1 on this face, and x3 is equal to minus 1 on that face. In other words, minus x3 is equal to 1, okay? And so what I want to say is that if I want to describe F, then I have to satisfy these inequalities, but some of them are going to become equalities. Okay? So let me say that, let me use the same notation that I had here. So I want to say that I have equalities for A prime and inequalities for the rest Okay? So what I'm saying there is that, for example, in this case, I'm calling these two A prime. So A consists of these 6 things. And I'm calling these two A prime. And I'm calling the other ones A double prime. Okay? So these are the 2 ways of describing a face. So what I would like to state now, and well, let me also finish by writing that A is the union of A prime and A double prime. And when I write a square union like this, I mean that it's a disjoint union. Okay, so this is disjoint. And V prime is a subset of V, so let me write V equals V prime union V double prime, where V double prime are the things that are not in V prime. Okay? So what I'm saying is I have a polytope P and its dual, and now I'm taking a face F in P, and what I claim now is that there is a dual face, which I'm going to call, then there is a face which I'm going to call F with a diamond here, or maybe let me say there's a corresponding face F diamond of the dual polytope with and now I'm going to write the description of F prime, okay? But before I write the description, let's look at this picture here and figure out what F prime should be, okay? And remember that the idea is that vertices here correspond to 2-dimensional faces here, 2-dimensional faces here correspond to vertices here, and so the corresponding thing to this edge should be an edge over there that kind of looks perpendicular to it. Okay? Can you see it? If you kind of stare at this picture long enough, you'll see that it's this one here. And it's kind of unfortunate that these things look like they're lined up, but actually they're perpendicular to each other, because really, if you look at where this edge would be in this picture, it would kind of go from the center of this face to the center of this face. So it's actually perpendicular to this thing. Okay? And how do I describe this face F dual? It turns out that it's as easy as just kind of copying what you did here. Okay? So I just go here and I say this was V, and so these were V prime. Okay? So I'm going to say, if I want the inequality description of F dual, all I have to do is write these inequalities and force these two to be equalities. Okay? And if I want to figure out what the vertices are, then I just do the same thing. I circle this, and you'll see that these are the vertices of this polytope. Right? For example, the vertices of this polytope are 0, 1, 0, and 0, 0, minus 1. Yeah? So that's the correspondence. So this is the convex hull of the rows of A prime, and it's the y's such that V prime x is equal to 1 and V double prime x, y is a row vector, and that means that I have to multiply on the left side for this to make sense. Okay. So this is putting into mathematical language what I'm saying here. Okay? Every face has a corresponding face here, and to get it, you just copy the same thing, and whatever was vertices here becomes inequalities, whatever was inequalities becomes vertices. Okay, and so this gives me a one-to-one correspondence between the faces of P and the faces of the dual. Okay, and now the other thing that I want to point out. Well, so there is a bijection between the faces of P, which I called L of P, and the faces of the polar or dual polytope. But the other thing that I want to point out is that consider, for example, this vertex, right? So this vertex, or maybe let's consider this one, because I'll actually draw the picture better if I choose this one. Okay? Consider that vertex and call it G. Okay? So what's the corresponding face there, F polar? Do you see it? It's the bottom triangle that's facing us, right? Which is why I moved G to be here, so that actually this thing is visible to us, and this is G diamond. Right? And the point that I want to make is that if G is contained in F, then G dual contains F dual. And this follows immediately from this description, because if G has fewer vertices, that means that here you have fewer inequalities, which means that you're bigger. And so that's why I left some space here, because I want to say there is an order reversing bijection between these things. And so what that shows. So I hope you did watch the lecture 2 times ago, where I defined or 3 times ago, where I defined the face poset. Right? So the face poset was the partial order of faces, ordered by inclusion. What this is showing is that if you draw the face poset of P, then when you turn it upside down, you get the face poset of P dual. Okay? In other words, L of P opposite is isomorphic to L of P dual. Okay? Which is one of the main results and most important results about the polar polytope. Okay? Any questions about that? Are you guys happy with this? Okay. So that's almost all of what I want to say about polars. Maybe I want to just say one last thing about this, and I need to make a definition for this. So, or 2 definitions rather. So one, we say that a D polytope is simplicial if every facet is a simplex. Okay? So for example, if we look at those 2 polytopes, the cube and the octahedron, is either of them simplicial? The octahedron is, right? Because the octahedron has as facets triangles, and triangles are simplices. Okay? So example, the octahedron, which I called like this, right? Diamond sub 3. And a non-example is the cube, right? Because the cube has squares as faces, and squares are not simplices. Okay? Equivalently, if you look at the phase poset, so let's say that this is the phase poset. Okay. Then this represents the faces of the polytope going up in order, right? So let's consider, so where are the facets? Well, the facets are the highest faces that are not the full polytope, right? So here's a facet. Okay. It's in the next to last floor. So then what happens if we look at the interval from 0 to f? Then we're basically looking at the faces of f, and f is a simplex, right? And we know that the phase poset of a simplex is the Boolean poset. So equivalently, I can just say that all of these intervals are Boolean posets. Another thing that I should point out is that if the facets are simplices, then all the faces must be simplices. Why is that? Because if you're a face, then you're a face of a facet. And if the facet is a simplex, all of the faces of a simplex are simplices. And so that means that not only are the facets simplices, but all the faces are simplices, which means that any interval from 0 to anything is Boolean. Okay? So another way of saying this is that every interval, let's call it every lower interval, from 0 to anything is Boolean. Okay? So these are equivalent conditions. So that's how we define a simplicial polytope. And I think actually Tristram defined this for you guys in his tutorial. So the second definition is that a D polytope is simple if every vertex is on exactly D edges. And so again, what's an example of this out of the ones that we have there? Well, there D is equal to 3, so in the cube we know that every vertex is on exactly three edges. But if you look at the octahedron, every vertex of the octahedron is on 4 edges, so that's a non-example. Now, how does it look in the poset? Well, a vertex is now something on the first floor of this poset, right? A vertex B. And now it's easy to see that if a vertex is on exactly D edges, then what you must have here is also Boolean. It's also a simplex. Okay? And one way of thinking about that is that if you just look locally at the vertex, okay, so you're in a big polytope, but you look locally at the vertex, and that vertex has exactly D edges. Okay, Now, what I'm asking you to do when I start at V is I'm asking you to look at the faces containing V. And that means that in this big polytope, you only need to look at what happens around V, and you can forget about all the other stuff that's over there. And if you look at only this little piece of V, and there's only D edges coming out of there, then the vertex figure has to be a simplex. There's nothing else that it could be. And that means that this is going to be a Boolean poset. And by the same reason, now if you look at any interval of it, then any interval of a Boolean poset is a Boolean poset, which means that this is going to be Boolean also. So this is equivalent to saying that every upper interval from F to the top is Boolean. Okay? And again, these are, just like these two are equivalent, these two are also equivalent. Okay? So then what's the other thing that I want to say about polar polytopes? And vice versa. It's an if and only if. Right? Because if every lower interval of... So, okay, let me repeat, because the students in Colombia didn't hear that. So a polytope... Let's actually write it. A polytope P is simplicial if and only if the dual is simple. And what's the reason for this? That if a polytope is simplicial, that means that the lower intervals are Boolean. So when you go to the polar, you're turning the poset upside down, and now lower intervals become upper intervals. Okay? So that means that the dual is simple, and vice versa. And this is why the hypercube is simplicial. That means that the cube is simple. And the fact that the cube is not simplicial means that the octahedron, did I say hypercube? Let me say this again. The octahedron is simplicial. That means that the cube is simple. The cube is not simplicial. That means that the octahedron is not simple. Okay? I took the red eye over here, by the way. I'm really exhausted. I didn't sleep last night, and I'm still here. That's dedication. Okay. Do you buy this? Yeah. You see that this is something that actually, if you look at the polytope definition, it's a little bit harder to see. That this is equivalent to this in the dual. But from the combinatorial description, it's very clear that if you turn the poset upside down, you can see that that's what happens. Okay. All right. So let's see how we're doing for time. Okay. So what I want to do now is introduce you to a beautiful polytope. That's my next goal. Okay. You're going to fall in love with this polytope. No, there's no way you can not do that. So the definition of the cyclic polytope might not be so beautiful, but you'll see that the properties are very beautiful. So this is meant to be a polytope with beautiful and extreme phase structure. And you'll see what I mean by that. When it comes to the phases of a polytope, this thing is as extreme as can be, and there is I mean that in a very concrete sense. Okay. So here's what I'm going to do. First, let's make it and I should also give a name to this thing. We're going to call it C sub d of n. Okay. So d and n here are natural numbers. Okay. And I'm going to define a polytope out of them. And so let's make a definition. The moment curve in Rd is the following thing. Is given by the image of this map. So let's consider the map from R to Rd that takes T to the column vector T squared up to T to the D. Okay. You should realize this is not at all a linear function. This is maybe the first non-linear, non-affine thing that we see. That's the moment curve. Okay. So for example, what is the moment curve in R2? In R2, it consists of the points t comma t squared. And so this is just the parabola y equals x squared. We have t squared, and so the moment curve in the plane is just the parabola y equals x squared. Okay. And in R to the cube is just something that kind of twists around more. So it's like t in one direction, t squared. So in the xy plane it's a parabola, but then in the xz plane it's the cubic t cubed. It's some curve. Okay. I can't really see it, but it's some curve. That's the moment curve. And what I'm going to do is I'm just going to pick endpoints on that curve. Okay. So the cyclic polytope let's write it like this, is the convex hull of endpoints on this curve. These points, x of t1 up to x of tn. Okay, so I'm just taking endpoints on that strange curve, and I'm taking their convex hull, and I'm calling that the cyclic polytope. And I guess I should choose n to be bigger than d, so that I have enough points to make a full dimensional polytope. Okay. So that's the cyclic polytope, and so what does this look like for example, d equals 2 and n equals 5. I'm just choosing 5 points on this curve, okay? So maybe I choose this one, and this one, and this one, this one, and this one, and I form the polytope. Okay? It's a pentagon. And in general, I do the same thing. Okay. So there's something, let's make an easy observation, but only in the case d equals 2 and equals 5 for now. You should realize that if you choose any 5 points on this curve, as long as the 5 points are distinct, the combinatorial type is the same. It's just a pentagon, no matter where I choose the 5 points. That's no surprise because in the plane, there's only one kind of n-gon, right? So that's kind of a boring statement. But the interesting statement is that for any values of n and d, the combinatorics of this polytope doesn't depend on what endpoints you chose. And that's what we're going to show, and that should be very surprising to you. I have no idea a priori why that's true, but it is true that if I choose n different points, you're going to get exactly the same combinatorics. Okay, so we will show this fact, the combinatorial structure, and by that I mean the phase poset doesn't depend on the choice of the points. And so that's why I just call the polytope C sub d of n, because really combinatorially it only depends on d and n. So we call this C sub d of n. Okay? But this is we need to show this. Okay? Question?
Is that equivalent to saying that they're all extreme points on that curve if you were to take its convex hull?
It's more than that.
Stronger than that?
So the question is whether this is equivalent to saying that each point is a vertex of the polytope. But I'm saying that actually, one thing I'm saying is that every one of these things is a vertex, but I'm saying much more. I'm saying that if there is an edge from here to here for one choice of the TIs, then there's going to be an edge from here to here for any other choice. It's a much stronger statement than that. It says, for example, that they have the same number of 7-dimensional faces, no matter what the TIs are. Okay. So I don't know if you're like me, you're wondering why one would at all choose that curve instead of any other curve, or why are we considering this strange curve, especially in a class on polytopes? It doesn't seem like that curve belongs in this class. Okay? And maybe what I'm about to show belongs less in this class, but we need it. So, or I should say, this lemma might not look like it belongs in this class, but it does, and we very much need it. And it says the following thing. If you take the determinant of the following matrix, no, sorry. So you're going to choose numbers A1 up to AD. And we're going to form this determinant. Okay, some determinant. Why does it have to do with what I'm doing here? Because if you notice, the first column is 1 and then x of a1. Right? This is exactly x of a1. This is x of a2, and so on. Okay. Has anybody seen this before? Maybe some of you have. It turns out that, by the way, so what does this mean? This determinant? Well, in principle, it's something very complicated to compute, because you're supposed to look at the d factorial permutations of these things. Then for each one, you're supposed to multiply the corresponding numbers. You're supposed to add up this alternating sign of plus or minus d factorial things and get an answer. That sounds very hard. But it turns out that actually this determinant has a very simple formula that looks like this. It's the product of aj minus ai for each I and j between 1 and d. Actually, I'm realizing something, which is that this matrix is not a square matrix. And if it's not a square matrix, then you can't really compute the determinant. So you see here, I have d plus 1, and here I have d things. So I meant to start at a0, actually. And now it's square. Okay? So this is a very strange result. It says that when you compute the determinant, which in principle is a big mess of plus and minus a lot of things, then for some reason, when you add and subtract these d factorial things, it factors beautifully, and you just get this. Okay? It's kind of hard to believe, but we're going to prove it. Okay? So here's the proof. Let's make the following observations. 1, the left-hand side is a polynomial in the AIs. Okay. That's no surprise because we're adding a bunch of powers of these things, so it's a polynomial. Okay? So that's the first observation. Second observation. If AI is equal to AJ, then the left-hand side has two columns that are equal to each other. And you know that if a matrix has two columns equal to each other, then that means that the determinant is 0 because that's a dependent set. Okay? So if AI is equal to AJ, then the left-hand side is equal to 0. Okay? And you know for polynomials that the only way for this to happen is if this is a multiple of AI minus AJ. So AI minus AJ divides the left-hand side. But that's true for any I and j. So third observation, if we combine this, we get that the product of AJ minus AI divides the left-hand side. Because clearly these things are these things have no common factors. AJ minus AI. So that when you multiply them all, that has to divide the left-hand side. And this is the right-hand side. So we have that the left-hand side is a multiple of the right-hand side. Now, why are they equal? Well, let's see what the degree of each side is. Okay, so that's what's the degree of the left-hand side and what's the degree of the right-hand side? Which one is easier? Can you tell me either one? You guys are being shy. You should know that in my classes you're allowed to participate and say things that are wrong because you might have noticed that I say things that are wrong. So if I can do it, you can do it too. So give me a wrong answer, please, and then we'll talk about the right answer. Is that right or wrong?
Can of worms you just opened.
So why d factorial? And is it the left or the right? So let's talk about the left. Okay, so what's the degree of this thing? So this determinant is a sum of d factorial things. Each term is something, and then there's d factorial of them. Okay. And what degree does each term have? But remember that, for example, what's one of the terms? One of the terms is multiplying this times this times this times this. Right? So it's not quite degree d, but I am multiplying d things. But the thing is that they have different degrees.
It's the sum of 0 and d.
It's 0 plus 1 plus 2 up to d. No matter what permutation you choose here, you're going to choose something in the first row that has degree 0, something in the second row has degree 1, and so on. And so each one of those terms has degree 0 plus 1 plus 2 up to d. So 0 plus 1 up to d. And how much is this? This is d times d plus 1 over 2. What about the right-hand side? What's the degree of the right-hand side? So why? I mean, one reason is because the theorem is true, but can you tell me, without using the theorem, why it's true?
Because you just have your running index there, and so you're going to multiply a d power times a d minus 1 power times and so on, but exponent if you add them together, so it's same as the sum.
It's actually even easier than that, because you're multiplying a bunch of things. Right? What's the degree of each factor? 1, right? Each one of these things has degree 1. And how many of them are you multiplying? The number of ways of choosing I and j. And how many ways are there to choose I and j between 0 and d? D plus 1 choose 2 because we're starting at 0. We have d plus 1 choose 2. And you have to hope that this is the same thing, and it is, right? So d plus 1 times d divided by 2 factorial. Same thing. Okay, so they have the same degree. If they have the same degree and this one is a multiple of this one, that means that the right-hand side must equal the left-hand side times possibly a constant. But if they have the same degree, the only difference can be a constant. And then the last thing we have to do is show that the constant is 1. Okay? And then the way we do that is we say, what's the coefficient of 1, a1, a2 squared, a3 cubed, up to ad to the d in the left-hand side? It's 1. It's 1 because it's the main diagonal, so that it comes with no sign. And what is it on the right-hand side? Again, you know the answer, but why is that the answer? What are we multiplying here? a2 minus a1 times a3 minus a2 times a3 minus a1 times a4 minus a3 times a4 minus a2 times a4 minus a1. Maybe let's just do it for d equals, oh, and I have 0, right? So let's do it for d equals 4, and then you'll see how it is in general. So I'm taking this, and I'm supposed to find the coefficient of 1, a1, a2 squared, a3 cubed, a4 to the 4th. Okay? So how can you, out of this multiplication, get an a4 to the 4th, a3 cubed, a2 squared, a1? When you multiply all of this out. Each one of these, when you multiply all of these out, what you're doing is that for each one of the factors, you choose either A1 or A0. Here you choose A2 or A0, A2 or A1, and you multiply all of this stuff out. Okay? How can this come out? You need... Let's start maybe with this one. How can you get A4 to the 4 when you multiply all of these things out? There's no other choice. You have to choose this, 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 and this, because those are the only A4s that are around. So you must be choosing those. How do you get this guy? You must choose this, this, and this. How do you get this guy? You must choose this and this. How do you get this? You must choose this. So there's only one choice, and it comes with a coefficient of 1. Okay, so this is 1 also. And that's why these two things are equal. I really like that. That's my favorite determinant, I think. Yeah.
Since it's 301, can I ask a question? Doesn't that have some also funky like Ehrhart polynomial property that cyclic polytope there? So this is like special in more ways than just discrete geometry.
Yes. So if you know what an Ehrhart polynomial is, then the cyclic polytope has one of the most beautiful Ehrhart polynomials. And that also belongs to this class. We're going to talk about Ehrhart polynomials later on. But what that means basically is that if you want to count the number of lattice points in this polytope, there's a nice formula for that. Okay. Let me just make one last statement about this, which is that if these numbers are different, that means the determinant is 0. Right? So corollary is that these numbers, these things are linearly independent, right? That's because the determinant is not 0. And we talked about how these vectors are linearly independent if and only if these vectors are affinely independent. Okay? Meaning there's no 3 on the same line, there's no 4 on the same plane, there's no 5 on the same space, 3 space, and so on. Okay? And that